Abstract. The rapid advancement of Internet of Things IoT technologies and artificial intelligence AI has opened new opportunity in transforming healthcare delivery, particularly for elderly monitoring. Falls remain one of the leading causes of injury and mortality among the elderly population, yet existing monitoring systems are heavily dependent on cloud infrastructures, resulting in significant response latency that can delay critical intervention. This report examined the integration of edge AI and IoT wearable devices as a solution to enable real-time fault detection with reduced latency by processing data at an edge rather than routing through centralized cloud server. The proposed system significantly improve response time, data privacy, and operational efficiency. Key technology examined include on-device machine learning models, inertial measurement unit IMU sensors, and low-latency 5G communication network. The findings suggest that edge-driven architecture present a technically feasible, scalable, and ethically sound approach to modernizing elderly healthcare monitoring systems.
The background of the selected issues is that the aging population and the fall risk. As the global population rapidly ages, the elderly fall detection has become one of the most critical and pressing challenges within the modern healthcare. And the next is the danger of the long lives. The fall are leading the cause of the severe physical injuries, but the danger is compounded by the long lives periods where an elderly person remains on the floor for a prolonged time without assistance. The threat to independence. These incidents not only cause immediate trauma but frequently led to permanent declines in health and a loss of independence and increased long term of hospitalization. So the solution is that while the current IoT frameworks relies on the traditional cloud computing, they suffer from the high latency that delays emergency responses. Adopting an edge AI addresses this bottleneck by processing data locally rather than on remote servers, ensuring the real-time response required for the elderly care. The objective of this report is that it is to analyze the technical drawbacks of the current cloud-based technologies used for detection, falls based on latency issues, and the data bottlenecks. Next is to evaluate the potential of an edge AI technology to decrease the reaction time and enhance the monitoring accuracy. Lastly, to assess the ethical and risk factors involved, especially concerning data security and healthcare technologies access disparities. The scope of the project is that this report focuses on the edge-driven AI for fall detection in elderly IoT wearables. It examines the transition from the cloud to edge computing to analyze the necessary hardware and software requirements and evaluate the socio-technological impact of this technology on healthcare.
The frequency of fall-related injuries in geriatric healthcare is becoming a huge crisis, which represents a leading cause of mobility and less independence among the elderly. The other complications are often referred to as the long life syndrome. So what is a long life syndrome? A long life syndrome can occur when a patient is unable to wake up from the ground for a long period that can lead to a rapid physiological decline, including a pressure-induced tissue necrosis and acute renal failure. The current monitoring solution often fail to address these issues because they rely on manual user intervention, which can be useless if the individual is unconscious or suffering from the cognitive impairment during the fall. So from an internet computing perspective, the main technical problems like in the existing cloud IoT architecture is firstly data transmission delay. So raw data collected needs to continuous uploading into a central cloud-based server that using up waste bandwidth and resulting in considerable latency. The second is processing bottleneck. So the centralized server processes numerous streams of data in real time that cause a delay in executing the algorithm for detecting faults. And lastly is false positive fatigue. Since there is no localized processing called edge intelligence, it becomes difficult to differentiate between a high impact fault and everyday activity of daily life, such as dropping the device or falling onto a chair. So this results in alarm fatigue among the medics and responders. So for this section, they have four stakeholders. For the first stakeholder is primary stakeholders, which is elderly people and vulnerable patients. So this category of stakeholders consists of elderly people that require an intrusion-free surveillance system. So for these people, the issue will be related to the trade-off between security and liberty. So in terms of technological needs, this device must be compact, portable, have long-lasting battery, and also high quality of experience. And for the secondary stakeholders is healthcare professional and emergency response team. So for the healthcare professional, they need a precise data logs, for example, heart rate at the moment of the fall to identify any possible causes such as stroke or syncope. And for emergency service, it depends on the reduction of false positive. So with the help of a digital society, alarm fatigue that stems from the malfunctioning of the sensor in that it considered a heavy item being dropped like a person falling down. So this can waste several thousands of man hours. And for the tertiary stakeholder, which is family caregivers, family members provide emotional and financial support. So their stakes lies in the real-time transparency as they have to receive push notification as soon as an anomaly takes place. And lastly is technical stakeholder, which is edge developer and network architects. So for the edge developers, they need to optimize the neural network so that it works on MC without draining the battery power of the wearable device. And for the network architect, they should make sure that if that even if detection occurs at the edge, the signal is conveyed via a strong low-power wide area network (LP1) or 5G slice to make sure that the data is uploaded to the cloud for storage. As we move towards becoming a digital society, integrating the IoT within our healthcare system becomes a structural imperative rather than being a convenience. So this project aims to tackle a key issues of AEL, which is ambient assisted living, in which technology will function as an anticipatory component of the safety of humans rather than be reactive in nature. So the idea of transitioning into edge driving AI is part of a larger chance in the direction of computing on a decentralized system that is necessary to provide healthcare in an area where society is aging. So the problem also relates to the issue of digital ethics. In today's world, more aware of the dangers of surveillance, that conducting any form of processing locally at the edge rather than sending this sensitive information to the cloud to ensure a certain amount of privacy. Resolving the problem of latency and detection directly solve the problem of establishing a framework in our digital society in which technology is used in the best way for human life and privacy.
Technology involved in this project are Edge AI and IoT wearable devices. Edge AI performs data handling right on the device or on a device close to the user. It decreases delay time as it is no longer necessary to send all data to cloud servers, which makes it possible to send alerts of emergency more quickly in case of fall. IoT wearable devices refers to gadgets worn by elderly people for monitoring their health. For example, are smartwatches, fitness bands, and smart medical patches. A commercial example is the Apple Watch. Sensors that are used in wearable devices are accelerometer that detects sudden movement or impact, then gyroscope that used for measures body orientation and posture, then heart rate sensors that used for monitors heart activity, and lastly pressure sensors that detects pressure changes during falls. Machine learning and edge computing. Instead of transmitting all raw sensor data to cloud server for analysis, Edge AI processes critical information locally on the wearable device or nearby edge node. This reduces response time and enables immediate emergency alerts when faults are detected. Machine learning algorithms such as convolutional neural network (CNN), support vector machines (SVM), and long short-term memory (LSTM) models are commonly used to classify movement patterns and identify fault incidents with high accuracy. Next, cloud and communication technologies. Cloud computing is still integrated into the system for long-term storage, advanced analytics, vision, history management, and healthcare provider access. The combination of IoT, Edge AI, cloud computing, wireless communication technologies, Wi-Fi, Bluetooth technology, and 5G, and machine learning creates a smart healthcare ecosystem capable of providing continuous elderly monitoring and rapid emergency response. The first causes of the problem is increasing healthcare demands. Older people are less physically active, have weaker muscles, suffer from chronic diseases and dementia, all of which make them more susceptible to falling. The fact that falls are one of the main causes of injuries and hospitalizations of older adults was stated by the World Health Organization (WHO). Conventional monitoring methods that depend only on the presence of caregivers or hospitalized patients are inefficient at most times since there is a lack of continuous time monitoring. Second is latency in cloud-dependent healthcare system. Traditional cloud computing systems rely on sending sensor data to distant servers for processing. However, this can cause network latency, especially in locations where the internet connection is not stable. During emergencies like fall, a few second delay could quite possibly worsen the injury and lower the chances of survival. The first impact of Edge AI and IoT wearable system is healthcare efficiency. It reduces hospital workload through remote monitoring. Second, faster emergency response. Real-time fall detection enables immediate alerts. Third, cost reduction. Minimize hospitalization and long-term treatment costs. And lastly, elderly safety. It improves independence and daily safety. The Apple Watch utilizes high-frequency accelerometer and gyroscope data to identify hard faults via proprietary algorithms. In the absence of a response within a certain time frame, the device automatically alerts emergency services and designated contacts. It benefits instant life-saving response without manual intervention. Every year, about 684,000 people worldwide die as a result of falls. On a global level, falls rank as the second most common cause of unintentional injury deaths. Those aged 60 years and over, the demographic who are most at the risk of sustaining severe injuries due to fall. This figure point out why effective real-time fall detection systems are essential for monitoring elderly people's health. To better understand the system architecture, this figure illustrates a typical HAI and IoT wearable healthcare monitoring framework, which first, wearable sensors collect movement and physiological data. Second, HAI device process data locally for immediate fault detection. Third, emergency alerts are transmitted to caregivers or hospitals. Fourth, cloud platforms store historical health records and analytics. Fifth, healthcare professionals remotely monitor patients' condition through dashboard and mobile application. This combination of HAI, IoT, machine learning, and cloud integration demonstrates how modern internet computing technologies can improve elderly healthcare monitoring by providing faster emergency response, lower system latency, continuous health monitoring, improve patients' safety, and better healthcare efficiency.
Proposed solution. To address the critical issues of fall detection latency in elderly monitoring system, this report proposed a three-part technical solution framework. The first component involves the deployment of edge computing infrastructures, which shift data processing from remote cloud server to local devices, dramatically reducing response time. The second component focuses the use of lightweight on-device AI models that are specifically optimized to run on low-power wearable hardware without sacrificing detection accuracy. The third component integrates 5G and low-latency network technology to ensure that alerts are delivered instantly to caregiver and medical personnel when needed. Together, these three solutions form a comprehensive, layered approach that addresses the problem from infrastructures, intelligence, and connectivity perspective. 4.1 Edge Computing Deployment. One of the most impactful solutions to the latency problem in elderly fault detection is deployment of edge computing infrastructures at or near the point of data collection. Unlike traditional cloud-based architectures, where raw sensor data must be transmitted to a remote server for processing, edge computing enables real-time computation to occur directly on local devices or nearby edge nodes such as smart home hubs or hospital gateway devices. This dramatically reduces round-trip communication time, which is critical in fault detection scenario where millisecond can determine whether an alert is delivered in time for effective interventions. Solutions such as NVIDIA Jetson models and Raspberry Pi-based edge nodes have already demonstrated viability in healthcare IoT deployment, providing sufficient computational power to run inference model locally without requiring constant cloud connectivity. This approach also improves system resilience and it continues to function even during network outreach, a significant advantages in rural or resource-limited healthcare. 4.2 Lightweight on-device AI model. A core technical challenge in edge-based fault detection is running accurate AI interference within the strict power and memory constraint of wearable devices. Traditional deep learning models are computationally expensive and unsuitable for deployment on low-power hardware. To address this, lightweight AI model architectures such as MobileNet, TinyML models, and quantized neural network have been developed specifically for edge deployment. These models are optimized through techniques including model pruning, weight quantization, and knowledge distillations, which reduce model size and computational requirement while preserving acceptable level of accuracy. For fault detection specifically, models trained on accelerometer and gyroscope data from Inertial Measurements Unit IMUs have demonstrated high sensitivity and specifically when deployed on microcontroller units such as STM32 or Arduino Nano 33 BLSNs. The use of TensorFlow Lite and Edge Impulse framework further simplified the deployment of such models through resource-constrained wearable hardware, making the solution practically implementable at scale. 4.35G and low latency network integration. While edge computing reduces reliance on network communication, certain scenarios still require fast and reliable data transmission. For instance, when an alert must be sent to caregiver's smartphone or a hospital monitoring dashboard, the integration of 5G network into the elderly monitoring ecosystem addresses this need by providing ultra-low latency communication of as low as 1 millisecond, high bandwidth, and improved network reliability compared to 4G LTE infrastructures. 5G also enable network silencing, which allow dedicated virtual network segments to be allocated specifically for critical healthcare application, ensuring that fault detection alerts are prioritized over other network traffic. In smart hospital environment, 5G connectivity combined with edge nodes created hybrid architectures that balance local processing efficiency with seamless real-time communication to remote caregiver and medical staff, making the overall system both fast and dependable. 4.4 Justification of purpose approaches. The purpose solutions are justified on three primary grounds: technical effectiveness, economic viability, and ethical soundness. From a technical standpoint, edge computing directly resolves the core latency problem by eliminating the network round trip to cloud server, with studies show edge-based system can achieve alert response times of under 500 milliseconds compared to 2 under 5 seconds typical of cloud-dependent system, a difference that is clinically significant in emergency response context. Economically, while initial deployment costs may be higher, the long-term reduction in hospitalization costs associated with untreated or late detected fault justified investment, as the World Health Organization estimate that fault-related injury cost healthcare system billions of dollars annually. Ethically, the shift towards edge computing enhanced data privacy by ensuring sensitive health data is processed locally rather than transmitted to third-party cloud server, aligning with regulatory frameworks such as CDPR and HIPAA, which impose strict requirement on the handling of personal health information.
The risks and ethical considerations. First is the data privacy and surveillance. The constant collection of data needed for the accurate fault detection presents an inherent contradiction between ensuring patient safety and respecting their privacy rights, which involves the data profiling risk, which the wearables generates a granular inertial data, accelerator, and gyroscope data that may unintentionally expose the patient's lifestyle through profiling, for example, walking peculiarities or routine. Next is the surveillance effect. Monitoring the elderly patient continuously could cause them a psychological stress, creating a panopticon effect whereby the users feel less dignity and autonomy in their own house. The mitigation against the edge. The solution for this is by adopting the method known as privacy by design. In this method, the use of an edge AI technology helps in processing the data on the wearable itself while only sending high-level event alerts to the cloud. Next is algorithmic bias and sustainability. Being an AI-based system, the system effectiveness depends on the quality of the training data, which raises the serious ethical concerns around the inclusion. First is the training data bias. Most fault detection algorithms are trained on young, healthy individuals mimicking faults. In real-world healthcare settings, this creates a bias that falls to detect the unique, slower falling pattern of the frail elderly patient, leading to the dangerous false negatives. Next is the environmental sustainability. The rapid growth of the internet computing fuels a high demand of a powerful hardware. Manufacturing and disposing of millions of IoT devices increases the electronic waste, while their continuous operation drives up the global electricity consumptions. Next is regulatory and compliance issue. Understanding the legal context is an essential part of a risk analysis in digital society, which is the data sovereignty and standards. The technology must align with the international regularities like GDPR and HIPAA. Health data must be securely encrypted, ensuring the compliance with the privacy mandates like the rights to be forgotten. Next is the liability and accountability. The inherent opacity of the AI algorithm creates a critical accountability gap. If the system fails to detect a fault, the lack of transparency makes it difficult to assign a responsibility among the hardware producers, software developers, or the hospitals. Social impact and mitigation strategies. The social implications that arise from this technological advancement need to be effectively addressed via proactive digital skill set and solution design. First is that to inform a digital consent, instead of the standard complex click warp agreements, the system should use a visual dashboard. This is to ensure elderly patients can easily understand precisely what data is leaving their devices. Next is the inclusive data set curating. This is to eliminate any algorithmic bias data must be proactively sourced from the real life words. Geriatric words. This is to ensure the system performs reliably across all mobility statuses and body types.
To conclude, the proposed model leveraging age-driven AI and IoT wearable successfully solve the problems of long emergency response times and low accuracy related to cloud-centric elderly monitoring devices. The use of distributed processing and real-time processing of sensor data right at the edge of the network provides significant improvement in response times that plays a crucial role in this project. In addition to solving technological problems, the transition from a centralized cloud-oriented model to the edge-based solution allows addressing some of the more fundamental ethical challenges arising as we move toward a fully digitized world. Local processing of personal sensitive information and data on a user's wearable device guarantees data security and integrity, which is vital in ensuring the individual's privacy and rights over their own data. Moreover, the use of specialized machine learning algorithms allow the decreasing false positive alerts and reducing medical alarm fatigue of practitioners.